Okay, welcome everybody. So today it's B-trees part 2, a brief summary of what we did. Last time we looked at this relaxed B-tree definition where a node may underflow. So basically that was this definition I showed, a simplified definition that overcomes the problems of this legacy that you have in typical B+tree definitions. So we have inner nodes, we have leaves. Inner nodes only have pivot elements, they only are routers to the underlying subtrees, to the underlying nodes, and the leaves contain the actual data. So the leaves contain key value mappings. The inner nodes don't contain values. That's an important differentiator of B+trees over B-trees. And again, recall, I will always say B-tree, but I mean B+tree in this lecture, as I explained last time. So we looked at point queries and range queries. So point query is just a matter of recursively going down the tree, just like in a binary search tree. Range query is a bit more interesting and a bit new, because what you do is to run a range query. Basically, you just do a point query first, run down the tree, and there you can scan over the leaf level. So a B+tree is two data structures superimposed over each other. One is a tree structure, and the other is a linked list of the leaves. And as you have the linked list over the leaves, you can do a scan over the leaves in both directions. Typically, you only scan from left to right, but in principle, you could also scan from right to left. So that's an important property of the tree. Then we looked at this tree inception. So the entire thing is a tree, is a B-tree consisting of a root node, which is an inner node here, another level of inner nodes, and then a couple of leaves. This is one tree, but you could also regard this as a nested B+tree in a way. So each of the subtrees in a B-tree is a valid B-tree. So these blue trees are subtrees, and they are valid B-trees in itself. That's a valid subtree, that's one, and that's one, and so forth. So if we enter the recursion, we see that even each leaf is a valid B-tree in itself. An important property is this key partitioning that these subtrees are doing. So the yellow, the overall tree, represents the entire range from minus infinity to plus infinity, the entire key domain. So here's some int or float domain. And each subtree represents a subset. So this is a subset from minus infinity to 43 excluding. And then including here is in this subtree 43 including to 91 excluding. So those are half open intervals. An important property here is that all of these subtrees on the same level represent disjoint intervals. So that makes sure that when querying the tree, you only have to run down one of the arrows, one of the subtrees. You don't want to run down multiple of these arrows. And that happens at all recursion levels. And we looked at the invariants and discussed a bit back and forth which to keep and which not to keep. And today it's about the split method. So that is one of the magic methods in a B-tree, and that handles the case if a node, if an inner node or a leaf node overflows. So what do you do with that? And how do you maintain the invariance of the B-tree? And one invariant we want to maintain here is that no matter which path you run down in a tree, it's always the same length, no matter which path you're running down. So it's a perfectly balanced trees at all times, like here in this picture. It cannot be that, for instance, here there's another inner node, and then that points to a bunch of leaf nodes. So this path here, if you run down 1, 2, 3, that would be 3 rather than 1, 2. This cannot happen in the standard B-tree. Again, you can relax that property, of course, if you want. That's okay, but we will look at a case where we maintain the tree such all paths starting from the root have the same length. And that happens in the split method. So the split method maintains this property. So if a node or inner node is full, we split the node into two new nodes. If it's an inner node that's full, we have to split it into two new inners. If it's a leaf node, we have to split it into two new leaves. So that's basically what the second sentence here is saying. And the split method has to partition the entries of the old node / leaf and distribute them over the two new nodes. And we have two implementations of this in our Python variant of that. And I would I will briefly show that how that works, and then show you a bit more of also on the slides. So I will mix the Python code with the slides a lot today. So this is a split signature. No, it's this button. So this abstract node, the superclass that defines the API of any node in the B-tree, has a method called split. And this is called if the node is overflowing, if it's too full. Yes, you want to insert something and you feel like, no, it's not going to happen. It's already full. I have to do something about that. And then this method is called, and that's implemented in the inner node and in the leaf node. And it returns some information that's called split happens. So whenever you call this, an instance of that is returned. And the idea of that is to signal, to provide information back in the call stack about that split. So the split happens instance will return the left node, the right node, and the pivot. So if you think about that along the slides, if we can go to a split already to show what happens here. Where do I have it? Which slide can I use for that? Maybe this is a good one. Yeah, maybe this is a good one. Yeah. So that's a situation like that we will be looking at. So basically, we have here we have here one node pointing to the leaf. Yeah, and then eventually we want to replace it by something like this. So there's one node, and there's two leaves now all of a sudden. Yeah? And that means that the node will also change. So here, see, I mean, previously you had one leaf representing a particular subspace of the data, and now that is split up into two intervals, into two leaves. And those intervals have to be split by a pivot element, and that pivot element has to be published to the parent node, and that's what you're seeing here. So this 45 is a new separator that wasn't here before, but now there afterwards, and that has to be known to this parent node. So the entire magic I will be using here is I will be exploiting the call stack of the B-tree. So if you have a tree like this, let's assume this is our B-tree, and I think that's enough as an example. And from now on today, I will write down time codes here. Why do I write down time codes? It allows me to join the picture here in video editing with the recording. Because last time I had 5 images, and then I had to find out which images belongs here. If I have the time code, this is a join key. Yeah, so each frame in the video recording has a timestamp. Okay. Now I take a picture with my phone, it has a timestamp, and then I join. What kind of relational join algebra operation is that? So I have all these frames, so 60 frames per second, each have a timestamp, and I keep each and every frame. And some of the time frames will be joined with such a picture. So what kind of join operation is that in relational algebra? And if I grin like that, it's probably a trick question. Yeah, kind of. Some inner join. I mean, the join key is not a foreign key ID kind of thing. So so let's say I have my video frames VF, yeah, and then I have this pictures P. So I'm not joining on a foreign key. I'm actually joining on an attribute called time. Yeah, time here. So basically, the join condition is something like that: VF dot time equals P dot time. Okay? So what if you do an inner join like that and assume this relation has one entry per frame? So what will be the result of that join if I join the video frames with the pictures I take? What is the overall result of that join? Well, how would the video look like on YouTube? Yeah? Yes, of course, you would only get those results, only those video frames that find a counterpart in a picture somewhere. So only that parts of the lecture where I scribbled something on the blackboard would be represented in the video. So that's not what you want to have. So how do you fix that in relational algebra? Yeah, so inner join is probably not the way to go. But there's a very, very similar symbol in relational algebra for that. No? Left, huh? But he was first, right? Do you want to say? Yeah. Left outer join. Left outer join semantics is no matter whether a video frame finds a match in here along the time join predicate, you will take it as part of the result anyway. So all video frames will be preserved. But if for some video frames you find a picture, you take the join result. Yeah, that's obviously union, inner join, union, video frames filled up with nonce. Yeah? So if you are unsure about that, read about that back home. Yeah? Okay, nice. But I was trying to explain this one. Yeah, joins and databases are everywhere. It's just you don't know about that. Yeah? Like you go out, yeah, you buy a coffee, it's a join, it's relational algebra. The entire world can be expressed by relational algebra. It's really like physicists look for the word formula. Database people already found it. I'm sorry, yeah? It's relational algebra. You can solve everything with that. So. Okay, but now we want to split this one. So assume those are our leaves, and that's the inner, which is at the same time a root node, of course. Now we want to split that. So the magic I will be using in the implementation, and that's a pattern you can use in any index structure you implement. Probably you used that already in binary search trees. Assume you want to do an insert. So you call insert here. Yeah? And what does insert do? Well, it looks for the appropriate subtree to insert the data value. So assume let's insert 42. And let's assume this represents, how do we do that? Let's say this is 50, and this is, whatever, 60. Now let's make that 30, right? Okay, 60, right? Did I miss anything? Maybe I should write something like this. It's more consistent. So we have two pivots, we have two keys here, and we have, of course, then three arrows going out to the subtrees. So if I do an insert 42, what do I have to do in this root node? First, I determine which subtree to follow, how to delegate this call down in the tree. This is an inner node. Aha, it must be here. So I go down here. Using our abstract node interface, this call here will be rerouted to the call underneath. And I don't have to know whether this is a leaf or node. Polymorphism does the job here. So I call insert 42, insert 42. I think in the implementation it's called put. Yeah? That's the same idea. And then I find out, oh, this is already full. My gosh, I can't put anything here. This is really terrible. So there's no room for that. So what can I do? In the implementation, I split this up into two new leaves. So basically this leaf, I have to be careful with my photograph, right? To take a snapshot. Doing an update in place, I have to keep the version lists in my multi-version store, otherwise I will be ruining the experience in the video. So I will delete this one. And replace it by two new leaves. One here, yeah? And then they're kind of half full. And depending on this split position, I put it on the left or put it to the right. But then there's a problem. Now I have one arrow. This knows about this one, but not about this one, the top level node. So I have to return the information that this was split. I split the original node into two. So this has to be propagated up. And I do that via the return code of the insert/put method. So the put method will return, hey, a split happened. And by the way, there's a new node here, and there are these two new nodes, and you should do something about that. So the split here will continue to change something in that node here as well. So assume that the pivot, the separating key here, now is whatever 50. Yeah, you have to propagate this new pivot up in the root node. And that means here you have to do something. You have to change this, yeah, to say, now this is 50. Now there's a new arrow to this new node, and the 60 stays as before, like this. Yeah, so this grows. There's one more key that's being inserted here on the top level node. Yeah? That's how a split operates. And an important property here is that you see the height was not changed of that node. Yeah? I didn't mess around with the invariant that the search path is always the same no matter what. Yeah? So it's always search path 1 here in this example. So I don't violate that. And if you look at that in terms of our code, then we will see how this works in more detail. So in the code, so we have this split happens information. That's exactly what I explained on the board, giving you the new left node, the new right node. And that is returned by the split operation. So if you now enter the put operation, let's assume, so you see it here, the put operation of the nodes returns exactly that, returns exactly that information. So let's look at the leaf. Let's now do in the code what we saw on the blackboard. So here's the leaf that has a put operation. Don't worry about this yellow. This is, I think it's a bug in PyCharm. I think it's correct in terms of typing, but PyCharm is marking it. So what does a put operation do? We get a key, we get a value to be inserted. We find the position, we find the wire binary search. That is what this is doing. So we look at the keys. There's a keys array in the leaf. We find the position where to insert. And then basically, if there's already the same key, that's what I'm trying here, what I'm checking here, if there's already this, if this key is already present in this leaf, I simply update the existing value. That is what happens here. And in this case, I'm not adding a new entry to the leaf, so I just return this information, no split. So whoever called put, yeah, who called put, the top node, the parent node called put, will get the signal, yeah, no split happens, I'm fine, I don't have to do anything about that. That's the idea. Yeah? Then I check here, this case, if the node is full. If it's not full, that means there's at least room for one key value mapping in this leaf. Yeah, so that's an easy case. So there's room for that. Then I can simply insert this into the keys array at the correct position. So the position determined above is a position where it should be inserted into the array. And that's what I'm calling here. Yeah? So in the keys array and in the values array, I put it in the right position, put everything that is there to the right, and then I'm good to go. And again, I'm signaling no split. I didn't have to split this leaf, so what? Yeah? Okay, but then there's a case we had on the blackboard, and that is this one saying, okay, the maximum capacity is reached. And watch out, so we are playing a little trick how you would do it in Python. If you did that in C++, maybe you would do it differently. So we check whether the node is full, and then we insert anyway. Yeah, so it's borderline, of course, yeah, because if it's full, so maybe you really can't fit anything there. If it's in C++, it's you have a page. A page is a storage unit, say, of 4 kilobytes or something like that. And if it's full, it's full. You can't insert there anymore. Yeah? But in Python, you have you have these lists. You can always insert and tra-la-la-la. So I temporarily live with a problem here that I'm adding one more element to the arrays than I should, than is defined by the capacity. Yeah? You could do that differently. That's how we did it to make it a bit simpler. Yeah? So I insert as before, and then I call the split method. And the split method will force the split of this leaf and returns 2 new leaves. So the existing leaf will be will not be used anymore, but the leaf that existed before will be replaced by two new leaves. Yeah, so you have in the split happens information, you have the handle to the left leaf, a handle to the right leaf, and the pivot element. That's the 50 I just explained. In this example, that's the 50 on the blackboard. And what I also need to do is recall that we have these pointers here in the B+ tree on the leaf level. Yeah, so they're pointing to the sibling on the left, and pointing to the sibling on the right. You could also implement fixing those pointers inside the split method. We don't do it, we do it outside. But now if you remove the old leaf and replace it by two new leaves, you have to fix those pointers. Yeah, that point to the left and to the right. And that happens here in this code. Yeah? This is all fixing the pointers. All of this code makes sure that the pointers point to the right positions. Yeah, and then I return the split information. In the stack, yeah, now if you look at, we can look at the node implementation of put. So here's, where's my, so the inner node, as we are calling it, or internal node, there are many names for that. So there's this put method. And that is what happens initially. So you call put on the root node reroutes it to the leaf splits it, and then the put method of the leaf returns the split information. You know, the split happens information. And that is what we have to check for here. So here, this is a rerouting. So I do the bisect, the binary search. Okay, I find the appropriate child. I reroute, so we're in the inner node here. I reroute the call to the leaf, and then I keep this information that's being returned. And then I check whether this information returned is a split happens or a no split instance. And depending on that, I have to make a decision. So if this is a split happens, what will happen in the case of the blackboard is, okay, oh yeah, there was a split happened underneath. That means now, so I'm here. I have to insert something here. I have to insert a new key here in my node, in my inner node at this point in time to fix it. Yeah? Otherwise, I mean, if you previously had a pointer here, I mean, you also want to have a pointer to this leaf now. So what do you do with that? So this is growing. Yeah? The node here, the root node in this example on the blackboard is growing. And that is what happens here. Yeah? And then, well, what could happen is, of course, recursively, it could be that, okay, now you're trying to insert a key here, but this node is also full. So you also have to split this node. So the splitting may recurse up in the tree. Yeah, so this might also be split into two new inner nodes. And that is the code you're seeing here. Yeah, so I'm checking whether this is full. And if that is the case, oh, I have to call split on this node here. Yeah? So if self is full, so where is that? Here I split self. That would mean the root node in this example. Huh? And then fix the pointers and stuff like that. But only then I return that. If there's room for the new pivot, I again return no split. And then whoever calls this knows, there was no split happening on this level. Yeah? And that's the magic you can exploit. Basically, I'm exploiting the call stack here. Yeah? I'm basically checking, I check the return of each of these methods. So all of these methods are about starting at the root, going down, and then returning. Yeah? So whenever you return from such a recursive call, you can check, oh, did anything happen I should know about? Oh, yeah, there was a split. Oh, then I have to do something. Yeah? And that's the trick in the implementation. Yeah. Okay, what happens if you split the root? Yeah?
I feel like at some point we have to add another layer to the depth.
Uh-huh.
Because all the inner nodes are full, so I think that's this case.
Yeah, exactly. So splitting the root is the only point in time where you increase the depth of the tree, increase the number of layers. It's the only point in time. All of these splits always happen horizontally. If you split this, if you split this, you don't change the depth. Yeah? That's a trick, basically. You add another leaf on the layer. The same happens here. Yeah? If you had more nodes on top, you split that. You don't fiddle with the depth. It's just adding another node on that layer. However, if this is the root node, maybe I need a new figure for that. So that's our root. And now we split. So basically, let's assume we're in this situation. Now we try to insert. We split the leaf. You feel like, oh, this doesn't work. You can't insert those 4 pivots with 5 pointers here. So what do? You have to split this one as well. That means I will end up in a situation like this. Yeah. And now what? I have basically this call here returns the split happens information with 2 pointers. The left is this, the right is that, and the pivot. That's information being returned. But yeah, now what? So what you have to do is you have to create a new root node. The pivot goes here, and those arrows go here. And that's the only point in time where you increase the depth of the tree. And this logic then happens in the put method of the actual tree, as I explained last time. So we have this design where the B plus tree is an abstract B tree and has an instance, so has a handle to the root node. So it's a decorator pattern, decorator design pattern, and the put method has to do exactly this check. So this is a put method of the B plus tree. So the put method has to check, oh, is the root, was the old root, is that split? If that is the case, this B tree is responsible for adding a new root. And that is what happens here in this case. So this is replacing the old root by a new inner node with exactly that information that is returned from the split happens information. That's how a B-tree grows. And in B-tree implementations, you sometimes also see inverse operations. So what is the inverse operation to a split? Yeah? Merge 2 nodes, exactly. Yeah? So you could, based on the constraint from the 70s, that it's, if it's less than half full, you somehow merge them. And that would do the inverse in the sense 2 nodes, there are actually many extensions of that where you merge 3 or 4 nodes. Yeah? But basically, assume you just merge 2 of the nodes into 1 node. The data is put into 1 node, and then you have to remove an entry from the parent node. Yeah? You could do the same thing in the implementation. We didn't implement that, but it's the same thing. Right, that's the inverse operation. And if the, no, that's the inverse operation. Okay. Right. So maybe we continue with this is just again the summary of the design principles I explained again already last time. But what we talked about so far was this point number 8. So the core stack of put handles those splits automatically. Return types indicate whether a split occurred. Yes? So I think the other things are already explained last time. And then let's look at more examples of splitting in a node. So here's a sample tree, an existing tree, and now you insert 50, 53, 55, and 58. Yeah? So I always show the start sequence here, and then I show what happens after inserting 50. So if I insert 50, I run down the tree, I end up in this leaf, I insert this in this position, everything is fine. Now I insert, so that's again repeating the state from the previous slide, just for convenience. Now I insert 53. Okay, now I have to split, because again I run down the tree, I see, oh yeah, that's where I should insert it. This leaf is full, so I can't insert it, so I have to split the leaf. So here this is the 2 new leaves that are created. Just a footnote, of course, you can also reuse the previous leaf, so you don't have to necessarily create 2 new instances. You could also keep the old leaf, remove some data, and put it to a new leaf. That's fine, if you want to do it like that. Typically, it's done like that. Okay, but now we're here, and you see we're inserting another pivot element here, so everything is fine. Yeah, that's okay. Here the insert operation stops. Now we are here, and now I insert 55. Right? They all insert to the right of the tree again, run down the tree. That should be inserted here. There's room for 55. Everything is fine. The insert operation stops at this point. So we're here. Now I insert 58. That happens here. So okay, I split the leaf here. I put 58 to the right in this case, and now what? That's kind of an awkward situation. So basically, I would have to do something here with a pointer and come up with a tree like that, probably. Maybe you create an inner node, but then how do you connect it to the remainder of the node? And that's the confusion you end up when implementing when implementing such a split operation. So if you do something like this, and set it to the smallest, use the pivot as a pivot, the 49, which is basically this element, this is not going to work because it doesn't separate the data. You see here 49, that should go to the right, and but here 49 is on the left, so it doesn't really work. It's the wrong pivot. So one hack for that could be to set the pivot to be 53. 53 would be the right pivot for this part of the tree, because it splits the 2 leaves correctly. It allows me to do the correct search. So 53 as a pivot means everything that's equal to 53 or greater is to the right. Everything that's strictly smaller is to the left. And that's what I'm seeing here in this tree. But here this is broken on top. That doesn't work. And this discussion basically leads to awkward code, and an important observation that you can... I have yet another example. Shall we go through that example? I think we can shortcut it here. Yeah. I scribbled over that one like crazy. Can I remove this? No, right? Here we go. So how you should actually approach a split of an inner node. So the split of a leaf node is kind of trivial. Yeah, you have your keys and values, you cut them in the middle in half. One goes to the left, one goes to the right. That's the easy case. Yeah? But when you split inner nodes, there is this problem with this middle element. And how you should approach that is, if you split a key array like that, basically what you're doing is you take the element, the pivot element in the middle, and pull it up. Yeah, that's what happens here. That's basically slowly pulling up the middle element, which is 45 in this case, pulling it up, removing it even further, and then using that as a pivot element in the parent node. That's how you implement the split. And you see that in our implementation, we do the same thing. When you look at the inner node split, here you see this mid plus 1. So basically, maybe first look at the leaf, because then you see the difference. In the leaf split, it's relatively easy. So you split the data into everything up to mid. Those are the keys up to this middle element. Yes, this is basically the length of the keys array divided by 2 in integer arithmetic. And then what you're returning is here, the left part of the array, and then the right part of the array. Yeah, super trivial. This looks slightly different in the node. In the node implementation of the split, here we are in the inner node implementation, you add this plus 1 on the right side. Yeah, so the left still splits till mid, and And here you have to be careful, this +1 is due to the children, and you have always one more child than keys. But here in the keys, you have this +1. And this is because the pivot is not part of the keys, of the key arrays anymore. So the element in the middle will be used as a pivot element. And that you see here. So this middle element will be returned up, yeah, to fix this problem. Yeah? And that's the right way of doing a B-tree split. Okay. Yeah, maybe look a little bit at this notebook. So, what? Control P. B-tree. Maybe a switch here. So I like this display in the browser better than the pie chart display actually. So that's why I'm using it here. Kernel restart and clear outputs of all cells. So what we're doing here in the notebook is it's a puzzle. We are puzzling the individual pieces of the tree into one B+ tree. Yeah? We don't start with an empty tree and then insert elements one by one. So in this notebook, we really do it manually. So we create individual leaves, and we do connect the leaves, hopefully correctly, create inner nodes, create the root node, tra-la-la-la, and then eventually end up with a hopefully valid B+ tree. And we use Graphviz, dot to visualize this. So I highly recommend whenever you implement an index structure to also write a visualization. That's not only for lectures, but also for debugging these index structures. It's super helpful. Yeah? If you visualize it and see, oh, the arrow is going in the wrong direction, or it's pointing somewhere where it shouldn't point to, stuff like that, you see it immediately. But if you have a textual output, did you ever see this textual output in the debugger of this nested nodes tree structure? Yeah, so that doesn't work. Yeah? Basically, it's hard to read. Maybe for small trees it works, but for larger it doesn't work. And another thing I recommend, and that's something I think I introduced this week. We didn't have it in the last lecture. That is, a B-tree has a couple of invariants. So I extended the API here to have a method in abstract. To have a method consistency check. That's already defined here in the abstract. Oh no, that's now I'm on the tree actually. Yeah, so the B-tree has a method consistency check, but it reroutes that to the root node, which has a method consistency check. And I implement that as both in the leaves and in the nodes. And in those implementations, now let's, for instance, go to the inner nodes again. I check tons of assert. Yeah? I check invariants, whether they hold. Yeah? I do that here on the node, and I know these invariants have to hold no matter what. Yeah? So an inner node has to contain one more child than keys. Yeah? That's what I had on the slides. I write that as an assert condition. Or I know that the keys should be sorted, because otherwise binary search is not going to work. This bisect operation be exploited. Yeah? Here in this implementation, we also do not allow for duplicate keys. Yeah? So I can basically create a set with each of the children here and check whether there's a duplicate with regards to that. Yeah? And then I recurse. In the inner node, okay, basically for each child in the inner node, I call consistency check on the children nodes. So if you look at the leaf implementation of that, you will see that, yeah, here again I check, okay, I have as many keys as I have values. I know that the number of keys should be smaller equal capacity, should be sorted, the keys. Again, there shouldn't be duplicates. I can check the isom links, yeah, to the left sibling and the right siblings. Actually, that is where we had a bug a couple of days before, and that's why, I was debugging the tree, and there was some weird error happening in some situation, and so let's check the invariants first. And actually there was a bug with the isom links. That's now fixed. Yeah, but you can recheck your assumptions about those links. Yeah? So I highly recommend doing something like that. And when you watch out, when you look at our tests now, we also exploit this method. So you don't have to call it in production, but when testing, we have test indexing, B+ trees, test B-tree and on range for a set again. Maybe you can check for references here. Yeah, so there's a helper method that creates a B-tree that is called, that's not the test method, but it's called by some of the test methods. Yeah, so you create a B-tree, and then this B-tree is tested. But what I'm doing is, every time I put something in the tree, I now call the consistency check, which is extreme, but is a good check for a test to say, no matter what happens in the put, yeah, the invariants should hold. Yeah? And if I break anything, here the test will fail already when trying to create the B-tree. Yeah? And that's, I think it's a good pattern to test your trees. Yeah? Okay, where was I? Right, yeah, now you can play with that, and it's similar to the example we had on the slide. So that's on initial B-tree. After inserting 50, you end up with something like that. Here the 50 was inserted, insert 55, and then the split happens correctly, and so forth and so forth. Yeah, that's maybe so far for that. Anything I wanted to tell you about? No. Okay. Another next thing we could think about is, how do you populate a B-tree with data? So again, if you look at the code, so where do we fill the B-tree with data? Do you remember? The answer is we don't. We're not using it. We have a Python dictionary. Yeah, but assume we use the B-tree. Yeah, so where would we instantiate such B-tree in our asset store? Where would we create an instance? Do you remember from last time? Yeah.
Maybe when creating the index.
Right, when creating the index. Yeah, that's what I showed last time. So we have this, if you go to stores, indexed MBCC, index transaction store, create index. So currently, this is hard-coded. There you could have a parameter somehow. They could be as part of the create index signature to say which type of index to create. Yeah? So if the flag is dictionary, then you do this index. If the flag is B-tree, you do this index, or you have a factory method of some kind. But here you could say, no, I am creating a B+ tree index now. When creating the index, yeah. But when you create the index, you run into index maintenance problems. Yeah, you freshly created the index, so the index doesn't know about anything, what happens in the store. So now it's a point in time where you have to scan the store. That's what happens here, and you index everything that is in the store send that information to the index. Yeah, for each and every entry, for each and every object ID / key value store entry, you somehow have to index that in the newly created index. Once you're done with those loops, the index correctly reflects the state of your store, assuming there's no concurrent modification going on. No? But assume here it's all serial for the moment. So this is the initial index maintenance you're doing. So when you look at this, basically you're looping over the entries from your store. And for each version entry you find here in this, yeah, so for each element in the committed list, you put something into that index here. Yeah, and then you do this check, does it have the attribute yes or no? And then but basically it does an index put. Yeah? So in other words, what we're doing is, new, whatever, file, blah, pi, cancel. So basically what's happening here is, for data item in store. That's everything is red now, of course, yeah. But what I'm trying to tell you is basically you loop over a ton of elements, yeah, and this could be, to make it consistent with the slides, for each of the keys, yeah. For each key in your array of keys, you put this key into the B-tree, yeah, and maybe some value. If this is whatever, you have key value items, of course, and it would be like key, comma, value, index, put key value. Yes, there's a loop here. You call for each key value pair to insert, you you call the put method of the index. And that's fair, that's correct, but it leads to a couple of problems. And maybe before going into this one, would like to give you some background. So in database systems, eventually you have to worry about how to store the data. It's an entire subtopic in database systems. It's called storage. We will be looking at that 2 weeks from now, so Wednesday in a week. Next Wednesday there's no lecture, there's a faculty retreat, but next week, Friday, there's a lecture that will be about machine-learned indexes, RMIs for short. You will see, interesting method. But the week afterwards, we will look into storage. And as I said before, storage is not as important anymore as it used to be, but it's still, you should know about that. And that's why we give a lecture on that as well. And I motivated my slides saying that the B-tree is so super versatile. You can adapt it in crazy ways. So this motivational slide I showed you last week, so this is an insanely versatile data structure, and it maps well to any type of storage. And just a brief outlook why that plays a role, and why that plays a role when trying to insert data into a tree. The question I just raised, you want to insert many, many data items into such a B-tree. Why could that be a problem, and how could you fix that? Yeah, so that's what we will be talking about now. So first, if you think about the B-tree, and why not use a binary search tree? I mean, you have these binary search trees. You talk about them in the algorithms and data structure class. And a big difference between binary search trees and B-trees is that, if you write a binary search tree here, that's a binary search tree. Those nodes are relatively small. You keep a pivot element there, maybe that has 4 bytes, and maybe you have 2 pointers of 4 or 8 bytes or something like that. Let's say it's all 8, then maybe it's 24 bytes. 24 bytes for any of those nodes. And these small sizes do not map well to computer storage. Not really. So in particular, and that is also one reason why B-trees got so popular, if you have a storage medium like SSD, or back then it was hard disks. So what these, the storage medium, we had that before, recall, that's a key value store. A key value store. That's what your file system is about, but that's also what all hardware is about. So what is a key? That is a memory address, for instance. In main memory, if you dereference the pointer, it goes to some memory, and then it gives you the byte or the word at that particular position. And that happens the same for SSDs and hard disks. Here the key is some number, say 42, and that gives you not only 1 byte, but typically a chunk of data, which is called a page. A page, like a paper page in a way. And this page is nothing but a bunch of bytes, typically something like 4 kilobytes. So 4,096 bytes. It's like you organize a book. A book is organized into pages. Your storage medium is organized into pages as well, not on paper, but based on these 4 kilobyte chunks. And we will see that when we talk about storage, but basically one observation here was that, okay, now if my B-tree doesn't fit into main memory, and at some points, or if my binary search tree doesn't fit into main memory, and I have to map these nodes to storage units, these small units are really awkward to handle because, okay, I could put multiple of those on the same 4 kilobyte page, But it's really awkward. So it would be much easier if I said, okay, that's what I have to live with. I have these 4 kilobyte units. Why not choose my node size accordingly to say, okay, an inner node has a size of 4 kilobyte max, no matter what happens. No matter which key types I store, no matter which values I store here, I would say, okay, that is one page. Maybe that's page number 0, page number 1, page number 2, and page number 3. Yeah, so you map your conceptual B-tree structure to the storage system by saying, okay, I don't choose the node sizes randomly. I choose them such that they fit on a page. Each node, that's a one-to-one mapping between those nodes and pages. So basically now you could say you have 4 pages here, this, and that. And that means when running down such a tree, the number of nodes you traverse also determines the number of pages you fetch from your storage medium, the number of calls you make to the underlying key value store, telling you, okay, please give me page 0. Then you find the appropriate child, and then, okay, give me page 3, and there you have the data, and then you answer the query, the point query. Yeah? So that's an important design decision why B-trees got so popular. And when you now blindly insert into a B-tree, it may happen that if the data is randomly distributed over the key domain, with every insert, you randomly insert somewhere in the tree. Yeah, so you have no locality. Yeah, it's very unlikely that 2 adjacent inserts hit the same leaf. Yeah, so if you have thousands of leaves, the likelihood goes down dramatically. So that's not very good in the storage system if you randomly insert data into a tree. So the question is how to improve upon that. And yeah, any ideas or any questions? So let's, if you go to our code here, yeah? So let's assume, where's my PyCharm? No, it's this one. Assume the keys here are generated randomly, yeah, by some random engine, or they're not sorted at least. They're not sorted and have some distribution. It's not sorted. Yeah? If it's not sorted and you insert one by one, you will be inserting at some random leaf, you will be splitting random leaves, blah, 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 blah. Yeah? So it will grow at some position with every put. In the worst case, you have to fetch one of those pages from disk. And fetching one of those pages from a storage medium comes with a price, typically. And back then, when these B-trees were conceived, reading such a page from disk was on the order of 20 or 30 milliseconds. Milli, not micro, not nano, milliseconds. This is insanely slow for a computer system. Yeah, assume when you compare that with main memory, we never worried about that. But if you do look up to this particular page, for instance, in main memory, this costs like nothing. It's some microseconds, nanoseconds, whatever. It's super fast. Yeah. But now, if this is not available in main memory, and you first have to fetch it from your disk, and you first have to wait till the data was shipped into main memory, that costs 20 milliseconds back then. Now it's faster. Now it's more like 3 to 5 or something like that on a hard disk. Yeah. But that means you can't proceed with your computation until the data is there. Yeah, until the data was shipped to main memory, you can't do something like that. Yeah, and that's a major concern in these systems. So if you now randomly insert in the tree with high likelihood every time, and here you don't have much main memory, with high likelihood every time you wait 20 milliseconds to fetch the leaf. Yeah, that's a high price you pay. Yeah? 5 milliseconds on a modern disk, 20 milliseconds back then. So how could you fix that? So you want to insert whatever, 100 million keys into an empty B-tree. How could you do that differently and more efficiently? Yeah?
The leaves are like some kind of indices, right?
Yeah, right. That's the ISM property.
First, load the leaves one page per time.
Mm-hmm.
Sort the leaves, something like a merge sort, but two segments, and after sorting the leaves, we have the leaves, and now we can build the try on top of them.
Excellent. Yes, that's something you could do. So basically you sort the data first, however you sort them, yeah, or you could also put them in the leaves and sort the leaves, but maybe I put it, maybe use the board here. Yeah, so you were saying, okay, those leaves are in a linked list. So you could create first a linked list of those keys and make sure that the keys are sorted across those leaves. Yeah, so you make sure that within the leaf the data is sorted, but also across the leaves, so everything here is strictly bigger than everything here and so forth like that. Yeah? No matter with some sorting algorithm. Yeah? And we will also look as part of this lecture as an outlook, what if you sort data that doesn't fit into main memory? So the stuff you learned about doesn't work. Yeah? Quick sort and merge sort don't work, but there are methods, one is called external merge sort, allowing you to sort arbitrary large data sets with super tiny memories. It's a very nice method that you could use here. So you sort it, and once you're done with that, you could create the tree. Yeah, over those leaves. Okay, that's what you were suggesting? Yeah, so that's a valid method actually. That's called bulk loading a B-tree. So not doing these one by one as shown here, but really having a separate method bulk load. And actually the interface already has that. So if you look at the B-tree interface here, it has a bulk load method. Yeah, the B+ tree has that. It routes to the superclass method. And what does the superclass method do? Well, it runs a loop over all items. I don't gain anything by doing that. You could run this loop outside the tree and just call put one by one. That's exactly what I did in this. If you go back here, that's exactly what I did here. Yeah? That's basically running the loop outside. So I have a fallback implementation basically here saying, okay, I implement the method with a stupid algorithm, which is looping over that. But if anyone wants, they could implement that with a smarter algorithm. And that would be something as what you explained right here. So you could basically sort the leaves and then create the tree and the nodes you need for that recursively to bottom up. Yeah? That's a valid method. That's called bulk loading. There are many more methods like that. Okay, good. If you don't want to fiddle with the implementation of the B-tree, so let's say you don't want to implement this. I mean, if you implement that, okay, sorting, you have to solve sorting, and then you have to fiddle the pointers, and there are some special cases. Actually, be careful that you can run into, and have to be careful to solve them correctly. So you have to implement something to implement the method, which is, yeah, it's okay, you can do that. But if you don't want to implement an algorithm, just using the existing API of the B-tree, is there anything you can do to improve the insert process, given what I just explained? Yeah, maybe someone else? Yeah, without implementing anything, can you do a one-liner that dramatically improves bulk loading the tree without implementing an algorithm?
I'm not sure, but what if we sort them and add them one by one?
We sort them and add them one by one. That's the correct answer. We first sort the data. So we sort the data and then insert it. So not as shown here. Again, assume, here's my, why can't I switch files here? That's weird. So, so what you're saying is, rather than looping over this stuff, we first sort on the keys. Yeah? So whatever items I have, I would call the sort method, and then I insert the keys along the sort order. So what is going to happen? with a B-tree. So it's a standard B-tree. How am I going to construct the B-tree? How is it going to look like? Or maybe let's make it here. Does anyone have an idea what will happen in the B-tree? I think I don't need that. Yeah, sorted, you insert a sorted sequence of data items. What's going to happen in the B-tree? 1, 7, 9, 10, 12, 14, 15, 16. So let's insert that. So how do I start? Let's say a leaf has a capacity for 2 key value entries. Okay? Yeah?
Basically, the leaves will be filled to their maximum capacity before creating new ones.
Yeah, right. So here I would have 1, 7, whatever value. Now what happens when I insert 9? You insert a new root. Yeah, so we would say something like, okay, I have to do something here. I have to create a root, and I have to redistribute the entries. And redistributing the entries would mean something like that. I put the 7 here. Maybe I make it 4, right? It's a bit harder to see if it's only 2 elements in the tree. Let's make it a capacity of 4. Then you see what I'm aiming at. So let's assume I think it was called n star capacity on the slide. That's a number of key value entries in the leaf is 4. So I restart to say, okay, we have 1, 7, 9, 10 in this leaf. Bum, 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 with whatever values, doesn't matter. I'm trying to insert 12. Hey, I have to split. Sure, that's what we just learned. What does splitting entail? It entails redistributing the entries over the 2 leaves. So which means 9 and 10 will go, for instance, here. Now I have 9, 10. This is empty. Okay, I have to create a node over that, an inner node, which separates this. So I would say 9 is here. And yeah, this is to the right. Yeah, that is a split. Now I insert 12. Here we go. So far, so good? Makes sense, yeah? Just have to, for your video experience. Okay. Now I keep on, so we were here up till 12. Now it's 14. That's okay. Now it's 15, so what's going to happen? I split it again. I redistribute 12 and 14. Bum, 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 bum. I amend this to have a 12. And what was I trying to do? I have this has to be removed. This has to be removed. And now I insert the 15. Okay. So far, so good. So what are you seeing here? What's happening?
Half of our pages are empty.
Always, huh?
Half of our pages are empty now.
Yeah, the pages are all only half filled, yeah, because every split removes half of the data, puts it to the right node, but then as you sorted the data, you will never ever insert anymore here. Yeah? After the split, you always insert to the right. Here you insert to the right. Yeah, so you end up with a leaf level that's only half full. Yeah? So this is unfortunate because the more leaves you have, the more inner nodes you have, of course. And, but however, in terms of I/O, it's still better because you operate on one page, you fetch it, then you take the next, and then you can forget about this page. You won't touch this stuff anymore, not even for reading. It's just a matter of always operating on these 2 pages and the root node on top, yeah? Like that, and then you shift to the right and stuff like that. Yeah? So it still has some advantages, but it's not as good as having a native bulk loading algorithm. Yeah? And as part of the assignment, you should actually think about how to do that algorithmically and how to fix, okay, now you have recursion, what happens if you go up and stuff like that. Yeah?
What if when we sort the data, first we add the keys on odd positions, and then we add all the keys on even positions? So we first have the odd pages, and then we start again and make them full.
Okay, cool, okay. So with odd and even, you would basically do 2 pass over the data. Yeah. So then first the odd. If you just take the odd elements, so that basically this, and that, right? Okay, so you would first insert 1, then you would insert 9 here, and then you would insert 12. You would still, in the second pass you fill up, yeah, it would work. I think it would work. Yeah, cool, sure. Yeah, but then you still have 2 passes over the input data. Yeah, so then you pay a price for scanning the input twice. Yeah, but you have the tree fully packed. Yeah, that's correct. Very good. Yeah.
For example, like this node will be half filled and half empty, right?
Yeah.
Just imagine.
Yeah.
So we'll be wasting the space anyway. But when it comes to the time complexity, for example, it will take, a very long time. Like you'll be traversing, like even the empty spaces as well, right?
When you mean when querying the B-tree?
Yeah.
Um,
Like merge sort has, like, I guess, if I'm not mistaken, n log n.
Yeah, it depends on what your underlying model is. Is it computational effort or is it I/O effort? We will also, when we talk about storage, so probably you typically when worrying about complexity classes, the question is what are the base operations you're worrying about? So if it's for instance you have an array and do binary search, you worry about the number of comparisons. That's fair. That's one cost model. But in databases, the cost model could be the number of these requests where I fetch something from the underlying storage. And that may be a completely different cost. Yeah, so if I cost that, and in particular with B-trees, then you can make like a 2-layered cost model because you want to understand, okay, what the heck, how long of a pass down to a leaf, which leads to the number of fetch operations from storage, so to say, and then you come in and say, okay, but now what happens inside a node? Yeah, the node is in main memory, and that's a standard cost model for doing binary search on that. Yeah? And then, of course, if it's smaller, it's not so great. It would be better to have longer arrays, of course. Yeah? That's true. Mm-hmm. Cool. Mm-hmm. Yeah, that's what I wanted to say about that one. Right. Okay. And now we will look at an extension of the B-tree over last time's B-tree. And that is available in the notebook. Where's my notebook? So now I'm using the B-tree for partitioning. And the observation is basically that the B-tree is creating what's called an equi-depth histogram or an equi-depth partitioning. Did you stumble over equi-depth as a term? It's basically you have, I don't know, you have a couple of stones or whatever, or data items, and you want to create subsets that have roughly equal size. That's relatively easy if you have a uniform distribution. Yeah, maybe I scribble it again on the board. So assume we have a key range here. That's your key range, say, from 0 to whatever, 1 million, 10 to the power of 6. That's a key range. Key range. And here's a count. And if you have a distribution which basically is uniform, then you can do what's called a histogram. So basically you split the range, let's say, into equal-sized buckets. You say at every, it's 1 million, maybe let's say at every 100,000, yeah, you make buckets. This is bucketing, so I should end up with 10 buckets. Not really, right? Should be a bit 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, almost. And then basically you can count inside the bucket how many elements are available in your data set. Yeah? And write that as bars, basically. Yeah? It's basically a bar plot. And then maybe if your data set contains whatever, 1 million elements, and now they're uniformly distributed, then you would roughly have something like, okay, 1 million elements, 1 million, divided by the number of buckets, which is 10. So you roughly have 10 to the power of 5, so 100,000 elements in each bucket, because that's a uniform distribution. Yeah? So uniform distributions only exist in statistics books and computer science examples. Outside, in reality, there's no such thing as a uniform distribution. I'm not aware of anything. Maybe some physicists correct me if I'm wrong, but as far as I know, it doesn't exist. Yeah? So you typically have way different distributions that are skewed, yeah? Normal distributions, Zipfian distributions, something like that. And then, if you do a count like this, you end up with a different graph. Yeah, so if, yeah, for instance, if you have data where you have more values in this part of the key space, yeah, same graph now, you do a count here, count, yeah, then you might end up with a graph like this. Yeah, whatever. That could be the histogram. Yeah? I mean, that's 1, 2, 3, 4, 5, 6, 7 buckets only, but even if you did 10 buckets, you would end up with something like this. And that's called a histogram. It's giving you information about the distribution, about a particular data set. And one property of a B-tree is that it creates a so-called Equi-depth histogram. And the idea, again, is to have buckets like here, where you roughly have the same number of elements within each bucket. However, now I'm fiddling with the size, with the width of those buckets in the key domain. Now I'm saying, okay, here, all of these buckets had the same width. And as it was a uniform distribution, that's going to work out. All of the buckets will have the same count. Yeah? But even with this one, I could achieve something similar. For instance, I could say I join these buckets, yeah, and form one super bucket, and then I stack the counts on top of each other. This as well here. Yeah, and then I make it, that is now my bucket. Yeah, and then it gets a bit more uniform here. Yeah, so that's called an Equi-depth. Depth meaning, depth really means here the number of elements in a particular bucket. And all the buckets have a equal, or similar actually, that's the goal. Equal is hard to do, yeah, but a similar number of elements. And the interesting thing is, a B-tree does exactly that, and that's what I'm trying to show you now. And that's very important for query processing, but also for understanding what the B-tree actually is about. And what I'm doing here in this notebook is, I have some data sets about latitude, longitude information about German cities. So, I don't know, I think it has 130,000 entries from German cities and villages. And then I basically load that information, but only use the latitude information. So this is one-dimensional. You can also do these things in a two-dimensional diagram. That also works. But let's stick for one-dimensional for the moment. And I compute the histogram. So what I just showed to you on the board. So here on the x-axis, you have the x information, the bucket information, the key domain as here. And on the y-axis, you have the count. Here it omitted the exponential somehow. Here you see it on the right. No, they didn't omit it. Okay. So what this is doing is now I'm looping over the sample size. So the distribution information you can compute by looking at each and every element in the data set, or you can draw a sample, a statistical sample that hopefully has the same statistical properties, and that's what I'm doing here. So I do that here and vary the number of elements I draw. So basically I take my original data. It's important to shuffle the data because if the data is sorted, you won't have the sample property anymore. And then I draw the top 10, 50, 100,000, 10,000, and 100,000 elements and create a graph like this and see whether the graph has a particular shape. So you see when I only draw 10 elements, you get a graph like this. If I draw 50, you get this, get 100, like this. And you see the more I draw, the less it's going to happen, shape-wise. You still see that the y-axis changes, of course, because the further you go to the right, more elements are used to create that histogram in the first place. Yeah? But you basically see that this distribution information, the histogram, becomes kind of stable after like 1,000 elements. So rather than taking all the 130,000 or whatnot elements in the data set, I just take 1,000 elements. Okay, so now with that information, I know taking 1,000 or maybe 2,000 is a good number. I create a B-tree. Standard B-tree as before. Also it's a bit big to plot, right? How can I plot it? I think last time it didn't work. Okay, kind of works. So the leaves are a bit full. I use very big leaves here. So you see the capacities I'm passing here is at 5 keys in the inner nodes and 2,000 keys in the leaf nodes, which means the leaves are super, super big. I have to scroll like crazy before I get to an inner node. Yeah? So in other words, I have a very small inner tree, a very small tree of inner nodes, and I have these super big leaf nodes. That's what I'm doing here. Yeah? If you maybe back home, you can scroll a bit to the right and maybe you find maybe if I go here, it should, here there's a node. Eventually we run into the root node here. Yeah? So trust me, it's a tree. It's just a bit wide. Okay. Now what I do is I convert this to something like this. So and maybe we first look at the implementation, then it gets a bit easier. Basically, I'm reusing our abstract node interface, and I'm introducing a new type of leaf node that's called a counting node. So that's again inherits from abstract node, and it doesn't store the data. The only thing this is doing is it counts the number of calls to the put method. So how many times does any parent node try to insert something into this leaf? That's all it's doing. Everything else is not implemented here. None of that's implemented except the visualization. So if you go back to our notebook, that's the call I'm doing here. This convert to counting leaf tree is now taking the tree I built up here, removes all the leaf nodes and replaces those leaf nodes by those counting trees. So this looks as follows. This is the inner nodes. This is the root node, and there's a second level inner nodes with all the pivot elements, and I'm removing all the data. I'm removing all the leaves stored in the and of course also data stored in these leaves, and replace each and every leaf with a simple counting node. Yeah, and that's the third type of node I'm introducing here in that implementation. And again, recall that I built this on the sample. I think I took 2,000 elements on top. Top for the best. No, 10,000. I increased it. Yeah, doesn't matter. You can. I think for 2,000 for this data it works very well. Even for 1,000, and then there's a cutoffs at some point. Yeah? So you see here. This is variant of a tree, of course, which doesn't store the actual data anymore. Now I insert the entire data set into this tree. However, recall that the put method here doesn't store the data, just counts the number of calls. So basically the information I'm getting here is, okay, if I inserted that here, or if I inserted data here, how much data would be inserted into this particular counting leaf? Yeah? And that's what I'm doing here. Then I can show it. And then basically, and what you see is here, so I actually adjusted the vertical extension of those nodes to reflect the number of counts. What you see here is that they all more or less have the same number of elements. So I end up with something like an Equi-depth partitioning. So the inner nodes here in this tree, in this example, serve as a partitioning function. They partition the data such that I end up with buckets, yeah, the leaves being the buckets, where the leaves all have roughly the same size and roughly the same number of elements. Yeah, see that? And that means that this inner structure of the tree, this root node and these other inner nodes, statistically or a model of the underlying data distribution. Yeah, they model how the data is distributed. Yeah, they model these intervals here from 48.223 whatever to 48.889. Yeah, this partitioning, you will see if you compute the difference, the distance varies. Yeah, the distance is picked by the tree and by the previous inserting of the sample such that the partitioning is Equi-depth. Yeah? And if you change that, of course, you would end up with different numbers. Yeah? But basically, this is done by the tree such that you end up with an Equi-depth partitioning. And that's exactly what you want to have with a B-tree. You partition the data equally. So this distribution, which was not Equi-depth before, so it's not uniform. You see that here, is now flattened out into buckets where each bucket roughly has the same number of elements. Yeah? And that's called the modeling property of a B-tree. Yeah? So the B-tree models, or the inner nodes, can now be taken as a partitioning function. For instance, you have a big data set and you want to partition that into equally sized chunks. You could create a partitioning function like that, throw away the leaf level, take this B-tree as a partitioning function, pipe all your data through that partitioning function, and then maybe you have, I don't know, 10 files on your disk that all these files have roughly the same size. If you didn't do that and blindly partition using a not so great partitioning function, you would end up with file sizes where one is 1 gigabyte and the other 1 megabyte and the other a terabyte or something like that. Yeah? So with that, you can create a partitioning where the files have roughly the same size. Yeah? So that's a very neat technique that you can use here with a B-tree. Okay, and finally, so now I'm introducing more node types here. Counting leaf, so we had the textbook as abstract node, inner, and leaf, and now I have a counting leaf. So what if we created a B-tree distributed over the internet? How would we do that? So let's assume we have 3 servers, and part of the B-tree, maybe the root node and 2 inner nodes sit here. And then here we have another part of inner nodes and leaf nodes. So basically this points here, okay? And this points here. So this is my B-tree, and each of these boxes are servers. Okay? So this is server 1, and this is server 2, and this is server 3. Okay. How could you implement something like that? And that's actually a practical way to distribute an index or a B-tree. Yeah? So you say for some reason it doesn't fit onto one machine, I want to distribute it over multiple machines. For whatever reason, that's how you could do it. What does it mean for the nodes you offer in the interface? I will have editing fun today. I can make it simpler. Yeah? I could even say, okay, let's assume this is your B-tree. Maybe then it's easier to say. See? And now this is mapped to a server, server 3, server 2, server 1, not to be confused with Amazon Web Services S3. What could you do in your implementation? Yeah?
Basically, you start, like one of the servers has to have the root node, so
Mm-hmm.
you can do whatever you want to put or you want to read something, you start there.
Yeah.
At some point, basically, the server's part of the B-tree is done, basically, and then
Yeah.
has to somehow track to whose server is it linked, basically.
Yeah.
And then basically it would just pass the value to the server and
Yeah, that's all correct. But let's make it more abstract. I said a tree is a tree of trees. A tree has subtrees, a subtree has subtrees. So this is a subtree, okay? And this is a subtree. So let's assume initially we have a leaf node that's mapped to one server. Yeah, and now we do a split. So if you look at our split operation, so the leaf splits it at some point here and creates two new leaves, B plus tree leaves, okay? So I'm hard coding which type of node instance to create here. What if I had an instance that's backed by a server? I could say at this point, I have a leaf that's backed by a server. This represents a leaf that's a server-backed B-tree leaf, server-backed B-tree leaf. So basically in the split, I don't return this main memory implementations, but server-backed B-tree leaves. Yeah, and of course, internally, they would map to a physical or virtual machine and do all the magic to distribute it over the network. Yeah, so rather than hard coding, what you do here, you could basically make this more flexible and based on certain situations, make a decision here. So do you know the design pattern for that? So here I'm calling an instance. Whenever you create an instance in your code, there's an opportunity for one specific design pattern. Did you hear about that? Anyone has an idea? It's always a situation like you do something in a method, and in the method you call a specific function. You create a specific instance. So that's the situation we're in. We have def foo, yeah, and then at some point you say a equals a. Yeah, so you create a new instance here. Yeah, and this can always be converted to what's called a factory method, factory pattern, meaning this function is called def foo with a factory, which is just a function. This is basically higher order programming, factory f. Yeah, and then you don't do this, but you do a is factory new instance. New instance. This is a method that's passed by the user from outside. Yeah, in our B-tree, this means you could have a factory here that allows you to be flexible on the types of leaves being created. Yeah, so if I have a function that I write as a user, and the function in some situation returns a standard B plus tree leaf, but I overwrite it in another situation to return a leaf that's backed by a server, I can use the implementation as is. I don't have to fiddle with this split operation anymore. Yeah? Like that, you could easily adapt the B-tree to run on a network of servers. Yeah? And the trick is really the factory method there. Okay, let's call it a day. That's it for today. Next week, Wednesday, no lecture. On Friday, we continue with indexing. See you then.